In this video, we're going to be talking about strong acids and bases and weak acids and bases, and specifically kind of how to find pH values for these things. So there are 7 strong acids that you need to know. So you would need to memorize these strong acids. So you should know the name, and then you should also know the formulas. And when you see them, know that when we say strong, what we mean is they go 100%. They go to completion. So they donate 100% of their H plus. Notice that we don't have a back and forth. There's not an equilibrium. If you have HCl and water, it is going to 100% turn into ions. So it 100% dissociation. No molecules left over. So you would not have any HCl molecules still together. It would be 100% hydronium, which is what this thing is called. So acids, when acids get with water, they're going to give their H plus to water. And when they give their H plus to water, we call this guy hydronium. Not sure if the previous videos had mentioned that or not, but that's the name of that. It's called hydronium. And it's just a polyatomic ion. Okay, so if we had the pH of a strong acid, basically, oops, I'm going to show you the first one and then I'll let you work the other two. So if we have the pH of a strong acid, we can just look at the mole ratio. So for every 1 mole of HI, remember pH is the negative log of H plus. We can think about H plus concentration, but in reality, H plus is really H3O plus or hydronium. So we need to think about in 1 mole of HI, how many moles of H plus are there? Well, if we look, there's 1 H in every 1 HI, so that would be 1 mole H plus, which would also mean 1 mole of hydronium, because they're a 1-to-1 ratio. So if we have 0.035 molar HI, I can rewrite that as 0.035 moles of HI over 1 liter, because molarity means moles of solute per liter of solution. Then I can just use my mole ratio. I can say for every 1 mole of HI, I know there's 1 mole of that hydrogen ion or hydronium, whichever one we want to look at. That's going to cancel out my moles of HI, and that will give me 0.035 moles per liter of hydronium, which we know is also 0.035 molar hydronium. And then we look at our pH formula. And we can plug this in. For pH math, the significant figures are the number of sig figs in the concentration equals the number of digits after the decimal for the pH. So we want 2 digits after the decimal here. So we'll type in our calculator negative log of 0.035, and we'll get 1.46 is our pH. So why don't you try part B and part C? So hopefully you try part B and part C. So answer for part B is 3.92. Answer for part C is 4.17. And these are both a 1-to-1 mole ratio. But you can imagine that if you had 2 H's, right, we would have a 2-to-1 mole ratio, and we would use that. Now, if you get to do this fast enough, you don't realize that you don't actually have to do anything besides multiply by the number of H's, right? So if you have a concentration and there was a 2 there, we would take that concentration, multiply it by 2, and then we could plug right into our pH formula. So if you do enough practice, you'll see patterns, and it'll cut your time a little bit in solving a problem. Let's reverse it. What's the concentration of HCl if it has a pH of 4.95? So I'm going to do the first one for you. and then you can do the other two practices on your own. So I want to know what's the concentration of HCl. And I have a pH of 4.95. Now we know that pH is equal to negative log of the H3O plus, the hydronium. Now with HCl, it's a strong acid, so we know that for every 1 mole of HCl, we have 1 mole of hydronium, because it's going to 100% 1-to-1 ratio dissociate. So how do I solve for the hydronium? Because if I solve for the hydronium, then we know the HCl will be equal to the hydronium concentration, because it's a 1-to-1 mole ratio. So I need to solve for the hydronium there. We're going to raise everybody to the 10, and I'm going to bring over the negative sign. So the hydronium concentration is equal to 10 to the negative pH. And I'm just going to plug that in. And so I get a hydronium concentration, which again is also my hydrochloric acid concentration. And remember that the brackets mean concentration, so that's why I'm just using brackets instead of writing the words concentration. For pH for sig fig rules, we have 2 digits after the decimal for the pH. That means 2 sig figs for my concentration. 1.1 times 10 to the negative 5 unit would be molar. So why don't you try for part B and part C? Hopefully you tried part B and part C on your own. Answer for part B, 3.5 times 10 to the negative 4. Answer for part C, 1.7 times 10 to the negative 3. Here's a list of strong bases. So we have basically any group 1 hydroxide, and then only some of the group 2 hydroxides. They will be strong bases. And notice that some of them have mole ratios where if you have a certain amount of this, you're going to have 2 hydroxides. So be aware of those mole ratios. So for every 1 of these, we might have 2 of the hydroxides. So just be aware of that. Make sure you can know the names of these things too, not just their formulas. So how could we calculate the pH of the following aqueous solutions? I'm going to do A for you. Remember that POH is equal to negative log of OH. So for 0.013 molar lithium hydroxide, that would be equal to 0.013 molar hydroxide, right? Because it's a 1-to-1 ratio for hydroxide. So what would the POH be? Negative log 0.013. We would type in our calculator, negative log 0.013. And we would get 1.89 as my POH. Why don't you try B and C? Remember for B though, there's a 2 there. So if you try B and C, hopefully you were able to recognize you needed to double the concentration for that barium hydroxide, because there are 2 of the hydroxides. So we should get a pH of 1.59. And for part C, you should get a pH of 4.04. All right, what if we have a pH of a solution, the strong base has a pH of 8.315? What is the original concentration if the base is sodium hydroxide and if the base is barium hydroxide? I'm going to let you try this one. So it's basically kind of what we did with the acids, but now we're talking about it with the bases, one with a 1-to-1 ratio and one with a 1-to-2 ratio. So if we have pH, hopefully you recognize this at the beginning, that's the negative log of H3O plus. So if we do 10 to the negative 8.15, we'll get H3O plus, not OH. So how can we change it to OH? So there are a couple options, but we can say POH is equal to 14 minus pH. Let me just grab what's the POH of that? So 14 minus 8.15. It's going to give me a POH of 5.85. Well, now I know the POH is a negative log of OH, and now I can find the OH concentration. You could also use the KW to do that, find the H3O plus, then use the KW. I'm going to raise everybody to the power of 10, bring over my negative sign. So hydroxide concentration is equal to 10 to the negative POH. Now I know my pOH is -5. My pOH is 5.85, so 10 raised to the -5.85. And I get a hydroxide concentration of 1.4 times 10 to the -6 molar. Now, for NaOH, that's a 1-to-1 mole ratio. So concentration of NaOH will equal concentration of hydroxide, which would be equal to 1.4 times 10 to the -6. That's my answer there. For part B, it's a 1-to-2 ratio. So let's look at 1.4 times 10 to the -6 mole of hydroxide per liter, because that's what molarity is, right? We have 2 moles of hydroxide in every 1 mole of barium hydroxide, because there are 2 OHs. So we would need to be dividing it by 2. Yeah, of course you can say that, oh, I just kind of can look at it and see I need to divide by 2. That's great, but most people probably can't do that. And if you don't trust yourself to be able to show your work to get credit on a test, I highly recommend that you find a way to show those mole ratios so you can get credit. Let me know if you have questions as you look at this. You can text me and I can help you out with it. Okay, so our main topic of what this video is going to be and what we're going to do in practice in class is weak acids and acid ionization constant. So acid ionization constant is a big phrase for equilibrium constant for acids. Okay, so it's the equilibrium constant for acids. So you notice in this generic equation, the equilibrium constant is products over reactants, but we don't include the water. We don't include solids and liquids. So you notice that the water is not in the equilibrium expression. The larger the value of Ka, the stronger the acid, which means the higher the K, the more it goes to the right, correct? The more it goes to the right, the more it donates. So the stronger the acid. And so what this is showing us here is that pH is not a good indicator of, well, pH can be a match indicator of acid strength, but pH really doesn't measure acid strength. Ka measures acid strength. pH really measures how much hydronium you have. And I'll probably talk about this in class for a little bit, but you could have, and this is only really able to do this comparison because we have the same amount of both. These are both weak acids, and so we can see that as the Ka increases, the pH decreases, so it gets more acidic. But you could have a weak acid with a low pH if you just have a lot of it. So I want you to kind of keep this in mind. Acid strength is not measured by pH. pH measures how much hydronium we have. Ka is where I get the acid strength value from. Here are some Ka values for some different weak acids. Remember, if it's not strong, it's weak. So you memorize those strong acids, and then you know the rest of them are weak. And these are just some Ka values. And if you know what we can do with Ks and we can do amounts, we can do ice tables, right? So this is nothing new. This is not new. This is just an application of what you've already known for ice tables. So if I tell you, hey, what's the pH of this much hydrofluoric acid? Well, hydrofluoric acid we know is weak. How do we know it's weak? It's not one of our strong ones we memorized. And what am I asking you to find? I'm asking you to find pH. What's the formula for pH? Formula for pH is the negative log of hydronium concentration. So what do I need to get pH? I need hydronium ion concentration at equilibrium. So basically, I'm asking you, what's the hydronium concentration at equilibrium? So I want to know, what is the hydronium concentration at equilibrium? We do the same thing we've done with any ice table, right? We figure out where our initials are, what our change is going to be, have our equilibrium, set it equal to that, put it in the formula, and we can get our X, which is the hydronium ion concentration, plug that into my pH. That's the plan. So why don't you try it first? Here's the rest of the work. Wow. So the rest of the work is a little bit wild here. So we would have our Ka is 6.3 times 10 to the negative 4 would be equal to x squared over 0.50 minus x. And so you can do these quadratic formula, but let's just use x as small. So if we use x as small, get rid of the x here, and then we can kind of move forward to do that. And then we get x is 1.8 times 10 to the negative 2. If that's our x, then we can plug that in to our pH formula to get our pH. And the shortcut is acceptable because if we do our x to see what percentage it is, we find it's 3.6%. They do it a little bit differently than I do it. I figure out what is the percentage of my initial concentration and is that smaller. But the same thing we've been doing with ice tables, nothing new. Just now we're solving for pH using the answer from the ice table. That's it. Why don't you try it? All right, so hypochlorous acid, HClO, reacts with, gotta write a reaction first. And so we're gonna write a reaction and say, hey, it's an acid, so it reacts with water. Make sure you know that's a liquid because it's not gonna be included. Then it's gonna make hydronium, and then what's the conjugate base? ClO minus, and these are all aqueous. My K, I always like to write the K out, would be H3O plus times ClO minus over HClO. All right, and then I can do my ice table. It's asking me for pH, which pH means at equilibrium, always. We don't really care about what's going on at the beginning. What I care about is what does it make at the end. Sorry, my writing is all off. I'm writing it kind of sideways, holding the iPad sideways. So we're not going to include water because it's a liquid. So we have our I, our C, and our E. They tell me that we start with 0.0075 molar of our HClO, which means we don't have any of our products, which means we must be moving to the right because we can't subtract from 0. Everybody's got a 1 mole to mole ratio, so it's actually not too bad as far as ice tables go. And we can just plug in to my K expression. So K is 4.0 times 10 to the negative 8, x times x over 0.0075 minus x. We can do x as small. So we'll take 4 times 10 to the negative 8 times 0.0075. We get 3 times 10 to the negative 10 is equal to x squared. Take the square root of both sides. And we get an x is equal to 1.73 times 10 to the negative 5. Let's see if it's 5% or not. So what's 5% of our initial? 5% of 0.0075. So we would do 0.05 times 0.0075. And I get 3.75 times 10 to the negative 4. So my x is 1.73 times 10 to the negative 5 is smaller than my 5%. This negative 5 is smaller than negative 4, so we're good to go. We can keep using x as small. So my pH is my negative log of my hydronium ion concentration, which is x. So I can just plug that in. So if you got the ice tables down, this is really just an application. If you don't have the ice tables down, then it may be a little bit more complicated for you, but just keep doing some practice with the ice tables to see if you can figure that out. So we would get 4.762 is 3 sig figs because our starting, well, actually this should be 2 sig figs, so it should be 4.7. Well, I'll keep the 3, but I'm going to round it to 2 sig figs so that my answer should be 2 digits after the decimal. Let me know if you have any questions by texting me, and I can help you out. We're going to do some more practice with this in class, of course. Percent ionization is basically of the amount you started with, how much ionized. Percent is always a part over a whole times 100. So my percent is the part that ionized over the whole acid, which would be the ion concentration, so the equilibrium concentration over the initial concentration, so concentration at time 0, which is initial concentration. Remember from when we're talking about rates, we put a little 0 at the end to mean initial concentration. Initial concentration of HA. So in this example, they told us if X is 0.0025, percent ionization would be 0.0025 divided by my initial concentration times 100. And that would give me a percent. So what's different here? So if we started with 0.1, our percent ionization was 2.5. Let's start with 0.05. So let's lower our concentration. Just kind of see what happens here. Lower the concentration and do the same percent ionization math, we actually get 3.6. So we can see that lowering the concentration raised the percent ionization. And so this graph kind of is showing me as we increase the concentrations, the percent ionization gets lower. So the smaller amount of acid that we start with, the more it will ionize, the more it'll break down. Why don't you try? Determine a pH and percent ionization for acetic acid solutions that start with these concentrations. So set up chart each of those initial amounts and see what happens to the percent ionization as you go. You're also going to calculate the pH. So if you feel like you're ready for some answers, solution A, you should get a 3.28. Sorry, solution A was 2.78 pH and 1.1% ionization. Solution B, 3.28 pH, 3.5% ionization. See how we are increasing our ionization as we decrease the initial amount. And the last one, we should have pH of 3.78 and a percent ionization of 11. Then, of course, if we are doing ice tables, we can kind of back into them as well. So we can actually use pH to figure out what Ka is going to be. So if I know the pH of a thing, then I could use an ice table to help me figure out, well, what are all the other numbers? So for example, if I tell you pH is 3.47, so what is the hydronium ion concentration going to be? 10 to the negative pH. So that's 3.39 times 10 to the negative 4. Remember, pH is what the concentration, pH is based on the concentration at equilibrium. So that's my equilibrium. And then they gave us our starting amount, right? And so if I know the starting amounts were 0 for my products, I know the end result, and that means the change must have been plus, so 0 plus what is 3.39 times 10 to the negative 4? Well, that's my change. Apply that same change here. So basically we said 0 plus x equals 3.39 times 10 to the negative 4. So x is equal to 3.39 times 10 to the negative 4. And so this one was plus x, right? This one was plus x, and this one was minus x. If we know that x is that, then we have 0.25 minus x equals what? 0.25 minus 3.39 times 10 to the negative 4 equals that number. And then once you have all three of these numbers, we're going to plug into K to solve for a K. So that's what we're doing here. Just once we have these three numbers, we'll plug in a K and we'll get our K value. So you can use K to help you find pH. You can use pH to help you find K. It's all just manipulation of ice tables. So here's an example. Here's a pH, here's the initial concentration, find K. All right, so hopefully you paused and practiced. So here's your ice table. I don't know why they did that. This should be 3537 here. So you should have a Ka of 3 times 10 to the negative 4. Or close by. They for some reason cut off that 37 there. I'm not sure why. Same thing goes for weak bases. Okay, but instead of Ka, we're going to talk about Kb. And again, it's just going to be the same thing. So ice tables and all that fun. So here's some practice. You know, you can go through this practice. We're going to do some of this in class. But there's some practice here. We're going to go through many of these in class, so don't spend too much time on them, unless you want to do both now and then also in class. But it's essentially the same ideas as what we were just talking about, but now we're talking about the base reactions. Okay. And we'll stop that here.